Okay, so I wanted to make a movie about how to set up the version 2.6 of the controller IC. For this I'll be using about 38 volt coming from 10S LiPo, 50 amp controller, and thanks to Izeman I got these innards from a Mac motor. And I'll be configuring the mode for Hall sensors. I'm starting with a completely empty controller IC, so no settings, preset, nothing. So this is the terminal program that I use. Let me see what focuses. Yeah. Okay, so to start, first we will set, the best is typically to go through the menus sequentially. So I'll start with by pressing 0 to change the mode to Hall sensor mode. First thing to set up, option A, the PWM. I'm using the board that is on endless sphere with 4 115s, and this will run at 21 kilohertz. Dead time is 500 nanoseconds for this setup, and then all I have to do is to auto-complete the loop sample frequency. Okay, for the current settings, the current sensors that I use are 50 amp, which have 40 milliamp per volt. The maximum phase current is 50. Battery current, I mean, I have a 10 amp fuse in there, so to make sure it doesn't blow, let's put 9 and put the regen to 0. And then the rest I can auto-complete again. And note that at the moment I start with 0 field weakening. What I typically do is I save it in between. So, okay, for the throttle setup, I'm using this slide potentiometer here. This is my throttle. Okay, so to calibrate the throttle, see, first it asks for throttle closed. So what I typically do is this is closed and then a little bit more. Then you press enter. See, and it has detected 870 millivolt. And now it asks for full throttle. So I move it to the full throttle setting. Press enter again and you see it detected around 4 volt. That's it. Then to activate this throttle and to tell how it should be used, it uses this polynomial coefficient. I typically just set them to 1, which means fully linear throttle, and the +1 means it's power current, not regen current. And I typically don't use any fancy second or third order shaping. So then left to do is, I'm not using the second throttle, I'll turn that off. And I'm not using CAN, so I'll also turn that off. To test the throttle, you can use option H. This basically shows what the second throttle is doing, the first throttle is doing, forward and reverse, and the position of the X shows the final phase current. This is throttle closed, forward, and you can see here as I open the throttle. This is the indicator for throttle 1, and then this is the indicator for throttle 1, or for complete throttle, using all the polynomial coefficients. And then I have a switch here in the controller, you can see forward, reverse. Okay, press enter. Let's just save it. Okay. Let's set the ERPM limits. Let's set forward 30 kilo and reverse also 30 kilo. Let's allow it to change direction below 150 ERPM. Transition at 1500 from drive. Drive 2 is Hall sensored in this case. Drive 3 is sensorless. And to go back, let's set it at 400. So what happens is that as the RPM increases, when it goes above 1500 it will switch to sensorless, and then from there on it has to drop below 400 to switch back to Hall. This kind of gives it some hysteresis and makes it more stable. Okay, battery, in this case 38 volts. Current sensor calibration. It only calibrates for offset, and typically this is not necessary. So with A you restore the calibration basically to 0, and that's typically good enough. Controller parameters, you can just select autocomplete. This is typically good enough. What I like to do, this option H, this 200, is the 200 is a value which is kind of this works with everything, but it is better to lower it a little bit to about 20 times I if your motor also takes this. And I know this motor takes it, so I'll typically use this value. Okay, filter bandwidth is just an autocomplete. The change with the previous version is now the speed filtering in the drive 2 is dependent on the mode. It's 200 millisecond autocomplete for sensorless and 50 for Hall. It spools up quicker if you use 50. Okay, then the motor impedance. Typically you can autocomplete. I find this value pretty high, it makes a lot of noise, so I reduce it a little bit to 8, and then with E it performs the measurement. I also put in an overflow indicator, because especially with this motor, with the MAH, it has a very high inductance, and if your current is too high combined with too high ERPM, with the supply voltage it will just not push the amount of amps, and then it will show the overflow. It makes a noise during this measurement. See, there was no overflow, and it saw 140 microhenry and 80 milliohm. About these values, these are for when you have a motor, when you draw it in star configuration. So with this particular setup, this one is 139 microhenry and this one is 80 milliohm. And then these are your 3 motor terminals. If you want to look at your motor in delta configuration, like this, then you can recalculate these component values from these. But the controller IC shows for the star configuration. Let's save it. Okay, CON, if you don't use it, you don't need to look at it. Recovery, I typically autocomplete, that's it. Hall sensor, autocomplete. And since this is the first time I'm running it, I need to calibrate, because here you can see none of the Hall sensors are known yet. So I switch on calibration. Temperature sensors, don't have them, switch them off. Miscellaneous is typically just an autocomplete. and then store. For the Hall sensor calibration to work, this online parameter save has to be on. If you switch this off, it will not go into calibration mode. If it's off, so save. Okay, calibration mode for Halls works a little bit different than before. It's now automatic, so you don't need to press buttons anymore for it to work. I'll just activate it and show you. Okay, this is my setup, so I turn that off. Not in setup mode anymore, then I reset. You can see here, the red one is drive 0 on the left, and then on the right one is drive 3. Now it's in drive 2 sensorless mode, because it wants to run its calibration. Now I just give it throttle. The mode is running, and to indicate the automated measurement mode, both drive 0 and drive 3 were on. It runs then for 4 seconds, and then all lights go on, which means that it's saving. And after it's saved, there's a reset, and now it's basically waiting in drive 0 Hall mode for the throttle to be closed, and now the controller is in Hall mode. Okay, put it in setup, reset it. Now the menus are back. If you now look in the Hall sensor menu, it shows here which Hall codes are used and at which degrees they are, and this is explained in the manual. What is new for this particular version is it indicates here the maximum ERPM it can reach for the battery, and it also shows the field shift when you use maximum phase current. This field shift, basically your motor generates a back EMF based on the permanent magnets, and the permanent magnets give a field which is like this. For instance, it's this direction, and the length indicates the amount, and so this is the field going through the stator teeth. And to make the motor run, what you do is with the coils you generate a magnetic field which is 90 degrees out of phase with this one, because then the perfect 90 degrees gives you maximum torque for your current. And if you put a little bit of current, your coil field is going to be like this. And if you put a lot of current, your coil field is going to be like this. And what these values here indicate is the max ERPM is a measure for the strength of your permanent magnets. If your permanent magnets have double the strength, the max ERPM will be half, because then your back EMF voltage is double and you can only fit half the amount of ERPM. And the magnetic field shift at full phase current is basically this angle here between the permanent magnet field and the coil field. And as you increase the coil field, this angle will increase, and for your maximum phase current you get a certain maximum angle. And this gives you a measure for how strong your coil field is with respect to the permanent magnet field. And I've included it in this version because what can happen is that, and this is strongly dependent on how your Hall sensors are placed, what can happen is that the Hall sensors see both your permanent field and your coil field, and then as you increase the coil field, the magnetic field will move, and it might be that your Hall sensors will trip next to the they will trip into the next position. And that what basically happens is your rotor is standing still, but the magnetic field moves. The next Hall position is triggered, and then this is no longer corresponding then with the actual motor position, and this then gives you a wrong wrong position information. So what it can do here in this particular version is it can compensate for this with this option C. If you set option C to 100%, it will basically compensate for the error in the Hall sensor information. But you only need to do this, of course, when your Hall sensor, when the Hall sensors also see the coil magnetic field. In this particular motor, the Hall sensors are not on the teeth themselves, but are in between, so it doesn't see this coil field, so you don't need to compensate for it. If you use optical sensors, they also don't see the coil field, so you don't need compensation. Same for when you have an additional magnet on the end of your motor shaft and you're using some other type of encoder, then also you don't need to compensate for it. The only time you do need to compensate for it is when the Hall sensors are placed in slots in the teeth. Then this value needs to be set to 100%, but the default which you get with the autocomplete is 0%, so no compensation. Okay, so this is the Hall mode now fully configured. I mean, basically reset. Put this forward, this reverse, and this is direction change. One other interesting thing now to show is the field weakening. See if it works. I have to reset first. Okay, so this is see, this is the 20 kilo ERPM the motor is able to reach with this particular battery voltage. This is torque current field weakening current. So if I try to break down the motor, you can see torque current goes up. RPM drops a bit and you can see power increases. Okay, now for field weakening, what we can do, for instance, let's turn the window back. Okay, so to the current settings, field weakening current here. If you want to use field weakening, I advise to use 70% of the maximum phase current. So in this case that will be 35 amps. Okay. Okay, set, and then let's just increase the ERPM limit just for fun. Okay, let's go to 40 and be both forward and reverse. Let's go to 40. Okay, now I reset to start this one. You can basically see now it reaches 40 kilo ERPM instead of 20. You can see this is I think I've shown that on endless sphere, but what happens with field weakening is normally you have your back EMF voltage, on top of that you have the resistor voltage, then at the angle you have the inductor voltage, and then this is basically the total voltage which is outputted by the controller. And under field weakening conditions, basically both the inductor and resistor part of the voltage standard angle like this, so they are rotated, and now instead of only this voltage, it fits this voltage for the back EMF. And basically the length here of the inductor part, if you increase this length to here for instance, you can see you can reach an even higher ERPM. And this length is given by 2p frequency inductor, and this is then the field weakening current. So if you use 30 amp field weakening current and the inductor was 140 microhenry, and this F this F was 40,000 ERPM, it was apparently reaching, so then divide by 60, so this is 600 Hertz, 666. So then if you calculate this voltage, it's 666 Hertz times 2 pi times 140 microhenry times 30 amp field weakening current. You get 17 volt extra. And this 17 volt is then, it kind of fits, because the 38 volt supply that we have means that, so you have 38, that your back EMF, when it rotates, basically can be 19 volt high. And on top of this 19 volt, we now get the extra 17 volt from the inductor and the field weakening current. So this 19 almost doubles, and this then also basically doubles the ERPM from 20 to 40. Okay, that's it. If you have this motor on your bicycle, then basically you're now finished with the setup and you can run your motor. So I hope this has been a useful video.